Hey guys, welcome back. And in this video, we're going to be talking about Newton's method. And I know at first, Newton's method can seem a little bit annoying because it has all these calculations in it, but we're going to find out that Newton's method actually isn't that difficult, as long as we're careful with how we input our answers. So let's go ahead and check it out. So first things first, Newton's method is used for finding blank, right? So we're actually going to use this method to find the zeros of a function, right? So we're going to put that in here. We're going to find the zeros or x-intercepts of a function, which are exactly the same thing, right? But not just any function, right? There's easier functions such as quadratics that we just factorable that to find the zeros, we just factor them and set them equal to 0. Those are the easy type of functions to deal with. In this case, we're going to deal with a kind of a harder function here, which we're going to call this function right here, f of x. This function to the right. We're going to try to approximate the zero of this function. And we're going to do that by picking, for example, this x-intercept, right? I want to find out what that x-intercept is. But how? Well, Newton's method is going to tell you exactly how to do that. We're going to use a random zero, which in this case we're going to call it x0 for being the first zero. The subscript tells you which term it is. And we're going to use the line tangent to that zero to approximate our x-intercept that we're trying to find, right? So we're going to use a bunch of line tangents, which are much easier to deal with than this kind of complicated curvy function, right? We like using line tangents, and that's actually all this chapter is about, how to apply the derivative. So let's go ahead and follow our x0 to its y-coordinate, which is up here, and then we're going to draw the line tangent to it, right? So if I have to draw the line tangent to the 0, I'm going to do my best, the best job I can in doing that. It's going to look something like that, right? So that means that I'm going to be crossing now. I'm crossing the x-axis at this x-intercept, right? And there's one thing that we can agree on here. We can agree that the distance between these two, right, between this blue distance right here, is a lot closer than this distance right here, right? So we've actually gotten closer to our x-intercept than before, right? By using the line tangent, right? But we're not close enough yet, right? We need to get even closer. So how are we going to do that? We're just going to repeat the same process, right? But before we do that, let's go ahead and name this guy. The initial point was x0. The point after that is going to be x1, all right? And then the point after that would be x2 and so forth, right? So let's go ahead and find the next one, which would be x2. So now I'm going to keep going down. And I'm going to draw the line tangent to that point, right? And that's going to look something like that. And I'm going to make that green. And now this green x-intercept is even closer to our 0, right? And we're going to call this guy x2. So you guys can imagine that if I keep going to x3 and x4, we'll be getting much closer and closer to my x-intercept. And that is the whole point of Newton's method, getting close enough to our x-intercept, right? And each term in Newton's method is called a what? So these are all called iterations, right? So the x1, x2, and so forth, those are all called iterations, which means that we're going to be doing that over and over and over again to try to get our answer. Now, Newton's method does fail in one scenario, and that is going to be when the derivative of x of n is equal to 0, which means that when the derivative of a term is equal to 0. But what does that mean? Well, when the derivative is equal to 0, that means that we have a horizontal line. For example, let's say here, the line tangent to that is going to be a horizontal line. Well, what does that fail? Let's think about it. Well, if we have a horizontal line, that line is not going to let us to a closer x-intercept because that line is never going to cross the x-axis, right? So you guys see how this red line right here and this blue line right here that we got, they both cross the x-intercept. So they got us closer to our 0. But let's say, for example, this red line here, the line tangent to that, would have been just a horizontal line, right? That would have never gotten us closer to our x-intercept because that would have been a horizontal line that just never crossed the x-axis, right? So that is why this case fails, right? And another way of looking at it is that whenever the derivative here is 0 in our formula, the function is going to be undefined. So that's no good for us. So now let's go ahead and go over the formula for just a second before we do an example. So the formula says that to find the next term, right, which in this case is going to be x of n plus 1, just the plus 1 term, the next term, we're going to need the initial term, in this case x0, and we're going to need to find f of that x of n, and we're going to divide it by the derivative of that x of n, right? And if that doesn't make too much sense to you right now, it's okay. We're going to go ahead and do an example on exactly how to use that. So let's go ahead and do an example. So here I tell you to find the fourth approximation, or x of 4, to the root of the equation x cubed minus x plus 7 equal to 0, right? So I'm telling you to find the root, or the 0, of this function. And then I'm telling you to start off with x1 equal to negative 2. So in this case, we're starting off with negative 2 as our first x value. So let's go ahead and do this. First things first, I need to actually identify my function, which my f of x is going to be my equation, which is going to be x cubed minus x plus 7, right? Then after that, I need to find my derivative. It's going to be 3x squared minus 1. So we're going to start off these problems by first identifying the function, and then we're going to go ahead and take the derivative, right? Because we need both the function for the top and the derivative for the bottom. So now, let's go ahead and put the formula together now that we have our function and we have our derivative. So when we do that, if we start here in x1, our next term that we're going to find is x2. So let's go ahead and do just that. So we're going to find x2. We're going to find x2 right here. And we're going to start off x2 by putting the initial term, right? Which in this case is going to be x1, right? I'm just going to do this for this one term just for it to make sense. F of x1, and then we're going to find the derivative at x equal to x1. So by doing that, I mean my x1 is equal to negative 2. So negative 2 minus f of negative 2 over f prime at negative 2. And now that means that I'm inputting negative 2 first into my function and then negative 2 into my derivative, right? So when I do that, I'm going to get these numbers. You guys can check this with your calculator. You guys are going to get a total number of negative 23 over 11, right? So you can say that when you compute this number, you're going to get negative 23 over 11, or in decimal forms, right? And we're going to put the decimal form here, 2.090909. So now I am done computing the second approximation, right? But what number should I use? Should I use the 23 over 11, or should I use the 2.09090909? Well, here's the deal. You want to be able to be as precise as possible, right? Which means you're going to leave rounding for the end. And fractions are the most precise it gets, right? These repeating decimals are not actually as precise as they could be. So we care about being precise. So we're not gonna use the decimal. We're actually going to use the fraction. So when I find here my third term, I'm going to go ahead and use 23 over 11. So I'm going to find negative 23 over 11 minus f of negative 23 over 11 over f prime of negative 23 over 11, right? And once you go ahead and compute those numbers, you're going to go ahead and get this ginormous fraction. Yes, you did it right if you got this ginormous fraction, which is negative 33651 over 16126. Or you could have gotten a decimal that gives you something like negative 2 point, oh by the way, this was negative 2.08675, and like more stuff, right? But here's the deal. Here's why I still recommend to use this fraction, because if you were to use the decimal, where do you cut it off, right? Do you just cut it off at the 8, but then you have a 6 next to it, so that should be a 2.09. Do you cut it off at the 6? Well, that'll be a 7 because you have a 7 next to it, you know? Do you cut it off at the 7? But that would be a, you know, that would be a 8. So you don't really know where to cut it off, so you're always going to have this error that you're taking in by just rounding off, right? So let's avoid all the rounding possible and go ahead and just go into using fractions, right? So we're going to go ahead and use fractions again. But I'm going to be real lazy, right? And I'm not going to actually rewrite that fraction again. When I'm finding my fourth term, I'm not going to rewrite my fraction because I already told you what that is. And you can do this for showing work, right? So I told you right here that, this giant fraction is equal to x3, right? So when showing my work to find this problem, I am just going to write here x3 minus f of x3 over f prime of x3, which means that I'm using x3 there, then I'm plugging in x of 3 into my function, and I'm plugging it into my derivative, right? So I'm being real lazy with extra writing that I don't need to do because it's going to save me all this trouble, this crazy fraction that I have. But I do recommend to use a fraction because if you use a decimal and you cut it off at a not so precise point, you're going to get a whole different answer for this part, right? So if you use decimals, try to use fractions as much as possible, right? And if you're going to use decimals, try to use as many decimals as possible. So when you compute this number now, it gives you an even bigger fraction, right? But we're not going to find any other term after the fourth approximation, so I'm okay with actually giving you guys a decimal. So I'm actually going to skip the part where I give you guys a ginormous fraction. It had like 12 terms on top if you use that giant fraction. And the actual answer was negative 2.086745, right? So that was what the fraction gave me. And that is my fourth approximation to my root of that equation. And now you may ask yourself, well, what is the actual root, right? How close am I from the actual answer? Maybe you don't care, and that's fine, but I'm still going to tell you. So the actual answer, the actual root, is negative 2.08675. And if we look at our answers, we're really close. The first four terms are actually exactly the same, right? The first four terms are actually exactly the same. And the only difference is this last term, right? But here I have a 5, and then here I have a 4, 5. So actually that 4, 5 will round to 5. So I almost even got the same answer by doing just 4 approximations, right? So the question is, when do I know when to stop if they just tell me to find the root, right? Well, you would stop whenever these terms actually start repeating, right? And you can actually see that here. Because here, the first two terms, see how, now let's compare these two terms, right? The first term is 0, the first term here is 0. So those two are the same. So they're one decimal place exact. Here 8, here 8, they're 2 decimal places exact. 6 and 6, so there's 3 decimal places that match, and 4 and 4, so these two are the same, right? So let's say I just cared about being correct to 4 decimal places. This was just fine because the first 4 decimal places of the two terms match, right? And then after that it gets a little different, but eventually you kind of have to adjust to how specific you want to be. So if you care about stopping at 8 decimal places, 9 decimal places, you look at that many decimal places. So that means that you need to have that many decimal places when you're rounding off. But I recommend to stay away from rounding off if you can. So that's when you know when to stop, when they actually start repeating and depending on how correct you want to be. So now let's move on to a different type of example where I don't tell you when to stop. So when you got to stop by yourself, right? And I actually don't give you a lot of stuff here. I just kind of, it's a whole different type of example. So let's go ahead and check it out. So here we have, use Newton's method to find the 5th root of 2. Correct to 4 decimal places. So what I mean by correct to 4 decimal places is just what I explained in the previous example. That the first 4 decimal places of the two terms, the terms you want to stop at, have to be exactly the same, right? And we'll see a little more of that when we actually get into the problem. So I didn't give you anything here. I didn't give you a function. I didn't give you a derivative. I didn't even give you a place to start. So this is a whole different type of problem. The first problem we can say was a little easier because it was just kind of like plug in stuff. But here we got to think just a little bit more. So we have to approximate this, right? So how do I do that? Well, this right here is a value. So how I'm going to start this, I'm going to set x equal to this value. Cool. All right. So now let me actually try to get a function. So how am I going to do that? I'm going to multiply. I'm going to not multiply, but I'm going to raise both sides to the third power. I mean to the fifth power. So I can cancel that fifth root there. Right? So now I'm going to get x to the fifth equal to 2. And I should do that in blue. X to the fifth equal to 2. Right? And I'm going to move over the 2. And now you guys can see that this right here looks like a function equal to 0. So I went from a number to a function, right? Which now looks very similar to this, right? I had a function equal to 0, and now I have the same thing. I have a function here equal to 0. Cool. We're good to go. Now, that means that my function in this problem is x to the fifth minus 2. Well, the next question is, what is my derivative? Well, derivative of x to the fifth minus 2 is 5x to the fourth. And now I'm done. I'm done taking my derivative. And now I'm ready to start with my Newton's method of iterations and all that stuff, right? So let me go ahead and kind of drop my formula over here. Just kind of like hang out here on the side, just so I don't have to scroll up and down. So it means that x of n plus 1, which is my second term, depending on where I start, is equal to the first term minus f of the first term divided by f prime of the first term, right? So just a quick check. I am right. So now I am missing one thing here, right? And I am missing this xn, right? This first term. Where do I start? Okay. So I'm approximating the fifth root of 2. So where do I start? Do I start like in 17? Do I start in like -5? I can't just pick any number. No, I kind of got to start somewhere kind of close by, right? So how do I pick this number? Well, this is what I do know, right? And this is how I would do this. The fifth root of 1 is equal to 1, right? That is a fifth root that I know, right? And the closest root to that I would try to estimate would be like 2 times 2 times 2 times 2 to 5, whatever the fifth root is that it gives me 2. Okay, so 2 times 2 is 4, times 3, I'm at 3 now, times 2 is 8, times 2 is 16, times 2 is 32. So it means that the fifth root of 32 gave me 2, right? So I see that the fifth root of 2, since it's between 1 and 32, has to be somewhere between 1 and 2. Now, who is it closer to? Is it closer to the fifth root of 1, or is it closer to the fifth root of 2? I mean, to the fifth root of 32. Well, obviously, 2 is much closer to this 1 right here. So I'm going to pick x1 to be 1. So my first term that I'm going to start estimating with is going to be 1. Because my root that I know is closer to 1, then it's closer to 2, right? So we can expect it to be like 1 point something, right? Rather than it being like 2 point something, because obviously it's way too big if it was 2. So that's how you pick somewhere to start, right? You kind of play with what you know, and then after that you kind of just pick something. So let's go ahead and get started. So that means that if I pick this to be my x1, I'm going to start looking for my x2, right? And how do I do that? I'm going to start with x1 minus f of x1 over f prime of x1. Now I just do this one to just start off, just to have the setup, right? The first term minus f of the first term divided by the derivative, of the first term, right? So if I do that, I'm computing 1 minus f of 1 over f prime of 1. And if you guys do that on your calculator, that will give you a total of 1.200. Or 6 over 5, depending on what you do want to do, right? But 1.200 is a dead ass decimal, so we're good to go. So now we try to find the third term. Remember that we don't know where to stop here. We just stop until we are 4 decimals correct, right? So now let's see what this term will give us. So 1.200 minus f of 1.200 over f prime of 1.200. That's actually going to give me, take a second if you want to do this, pause the video, take a second and do this on your calculator and make sure you're doing it correctly, because calculator work actually is annoying and gets people wrong answers a lot of times. So 1.1529. You see, I'm only rounding to the 4th decimal place, so I can compare just the first 4 decimal places, right? So now I'm going to go ahead and find the fourth term. But why do I do that? Because I can obviously see that between these two numbers, only not even the first term are the same. Here my first term is 1, here my first term is, here my first term is 2, and in my third term, my first term is 1. So I'm not even one decimal place correct, right? So I'm going to go ahead and find my next term. Hopefully, it's somewhere a little closer, right? So I'm going to go ahead and do that. And I'm going to go ahead and put 1.115, 29 minus f of 1.115, 29 over f prime of 1.115 of 29. And if I compute that, take a second and do it on your own calculator, it's going to give me 1.1487. So now I have made some kind of progress, because from here to here, only the first terms are the same, right? But the second term, you see I have like a 5 and a 4, so I'm obviously getting somewhere closer, right? That gap is kind of closing. So now, I'm still not done because I don't have my fourth places, so let me just go ahead and do another term, right? I'm going to do a fifth term, and I have a little bit of space there, so let's go ahead and do that. So I'm going to go ahead and put 1.11487 minus f of 1.11487 over f prime of 1.11487. And that is going to give me 1.11487. And hey, look at that. The first four terms are exactly the same, so I can actually call it a day, and I am done. I am done, right? I used it to find the root of the fifth root of 2. So I can say that the fifth root of 2 is equal to 1.1487, right? So this right here is going to be my root, my fifth root of 2. And if you do it on your calculator, you're going to get something extremely close. So, and because there's the fourth first place are the same. So now let's go ahead and do some practice problems on how we can switch up the Newton's method and see different variations of it, right? So, see you guys next time.